Okay, and now it says recording, so I assume it's working. I'm going to share screen here. Share. Okay. And you guys should see that now. Do you see it?
Yes.
Give me a thumbs up. Okay, great. Well, good morning, everyone. It's good to be back teaching this semester. Wish it were in person, like the first semester I taught, but I guess that's coming soon. Hopefully, maybe the I don't know, maybe the fall we'll be able to have in-person lectures again. Keep your fingers crossed. So the topic of this part of the lecture is on lightweighting, structural synthesis, and structural optimization of the primary structures for called them transportation systems now. So bicycles, cars. I think there's most of the focus on this lecture is on cars and bicycles, but the topics and the principles for the structural optimization and lightweighting could be applied to boats. It could be applied to trains, roller skateboards, roller skates, all kinds of things. So it's a pretty universal topic. A lot of the principles I'm going to talk about were really developed for aerospace, going back to like NASA in the 50s and 60s. So I've broken the lecture up into about 6 modules. The first one I'm going to talk about today, and I'm going to talk about what's important about lightweighting. Why are we interested in lightweighting? Why does society spend money developing lightweight materials and structural optimization methods? And then I'm going to talk about design of materials for lightweighting. So this is kind of a relatively new concept in materials science. When I say relatively new, I mean maybe the past 20 years. The idea that you can design materials rather than just picking materials out of a catalog, you can design materials for performance, whatever you need them to do. And this is tied in with the National Materials Genome Initiative started by Barack Obama. I'll talk about that more later. And it's tied in with the ICME initiative, so Integrated Computational Materials Engineering. That's going to take a couple lectures. This time I'm teaching the course, there's going to be more lectures in that area than there had been previously, because I thought maybe I was neglecting it and needed to talk more about that topic. But after we're talking about designing materials, we're going to sort of shift gears and talk more about the mechanical design portion of this. How do you design beams or structural members of a structure, of a car, of an airplane, of an oil rig, something, whatever it is? How do you design structures so that you get the lightest, most structurally efficient design? And we'll talk about what I call the constitutive laws of lightweighting. The next topic after that, module 4, involves more numerical optimization. So you guys have probably seen this before. You have some multi-dimensional design space. It could be more dimensions than you can fathom with your human brain, many thousands of dimensions. And there are ways, mathematical methods of finding optimum, finding maximum, finding minimum. These methods, these numerical methods, have been developed over, I don't know, many years, many years. People have been looking at this. There's lots of people who spend their whole career worrying about numerical optimization. In fact, some of these people are really nerdy. They have like competitions to see who can find places in a design space the quickest, who can write the best algorithm that gets you to the maximum or minimum. Talk a little bit about finite element analysis. A lot of the tools that are used for structural optimization are based in finite element analysis. There's the 3T tools, the topology, topometry, topography tools that I'll talk about. These are tools that are used that help you find, well, I say this, they combine finite element analysis with numerical optimization to find optimum designs, whether that's lightweight or for natural frequency or whatever structural concept you're looking for. And then the final module is module 6. And in module 6, I'll talk a lot about, I don't know, just tying together maybe some topics that seem to kind of, not random, but maybe they sort of are stray, they're out there. They're important to lightweighting. They're very interesting, but they don't necessarily fall so neatly into place with the other modules.
Let me just say that when you say modules, your modules are like 2 lectures each or so. Whereas my modules, when I say modules, and the students have to take 6 modules, that's an average of 6 lectures each for 36 total.
Okay.
So
Yeah, I didn't mean to confuse things. It just I was writing date lecture number, and the problem is that it was just really struggling to keep up with the days. Like some days they would get lots of questions and wouldn't finish things, and that's good, but it just meant the lecture number got screwed up. So I decided to put module instead. Okay, so really important. This is really critical with my lectures. When I was a student, I was a very poor passive learner. I was really bad at listening to people, and I didn't learn much. I just had to talk, which was pretty stupid. But the point being that that it's a lot of people, including me, are better at learning when they're active rather than passive. So ask questions. If you don't understand something, ask a question. If you want to bring up a particular topic, maybe I didn't bring up, then just ask. Go ahead. I want this to be a back and forth. I want this to be an interactive lecture. I've baked in a lot of time, I think, into the overall course to allow for questions. So please ask as many questions as you want. Okay, deal, guys? Good, okay. Okay, what is light weighting? What is light weighting? So a lot of people who work in aerospace and work in the automotive industry seem to very intrinsically, or they seem to, let me try something here actually. How do I do this? Is that better? Can you guys see that better now? You still see it? Thumbs up? Okay,
Yep.
great.
Works for me.
Works for you. Okay, so what is light weighting? So people in the automotive industry, people in the aerospace industry seem to be very comfortable with this term light weighting. You could probably tell from the previous slide that the dictionary doesn't have the word light weighting in it. So I think it's possible that people outside of aerospace and automotive maybe aren't so comfortable with that term light weighting. But light weighting is the study of trying to reduce the weight of a structure. So it's lighter, but it still meets all its requirements for strength or stiffness or corrosion resistance or whatever the design requires for whatever the specifications are. Stiffness, safety is an important one, obviously. It's kind of hard to pinpoint exactly when people started thinking about light weighting. I'm sure there was people in ancient Greece who were, I don't know, carrying around pots or clay pots or anything, and they said, God, this is too heavy. I wish this thing didn't weigh so much. And they probably thought of ways to reduce the weight of the stuff they were carrying around. But the literature discussion on light weighting or the concept of maximizing structural efficiency seems to start in the late 1700s with balloons. Okay, so back in the late 1700s, I'm going to screw up this pronunciation, the Montgolfier brothers from France, they experimented with balloons, and they tried to go higher and higher into the atmosphere. I think they might have been flying, sort of around Paris there. I've seen pictures where they've kind of drawn these, there's been drawings of like what they saw from their balloon, but they found it very quickly that the less mass you had on your balloon, the further up in the sky you could go. So I think that was maybe the first sort of organized, concentrated effort to reduce the weight of a structure, but they couldn't go too far, right? Because the balloon actually had to have some structural integrity, or the gondola had to have some structural integrity, so they wouldn't fall out the bottom. They got pretty high. I think they got as high in some cases back then as like a couple tens of thousand feet, maybe 10 or 20,000 feet. But that's kind of the first, I think, kernel of light weighting, people trying to make lightweight, efficient structures. It's interesting. One neat effect of light weighting is that as you reduce the weight of something, you can start reducing the weight of other things. So they call this the mass compounding effect. And what it means that, for example, if you have a car and you start off the car that's got a big V12 engine, okay, it weighs 700 pounds. And then you find a way with time to get the same horsepower out of a turbocharged 6-cylinder, let's say, or a turbocharged i4 engine. And then all of a sudden your weight goes from being 700 to 300. So the vehicle was originally designed so the engine would fall out when you hit a bump when the engine weighed 700 pounds, but now it weighs 300 pounds. So you can reduce the weight of the body structure. When you reduce the weight of the body structure, then you can start reducing the weight of the suspension components. When you reduce the weight of the suspension components, you can put lighter, smaller wheels on. So there's sort of a downward compounding effect. But there's also a converse to this, that as you start adding weight to things, as you start adding bigger engines or more accessories in a car, or air conditioning, or I don't know, whatever you might add, the weight of the vehicle goes up more quicker than linear. It starts to compound on the way up too. So there's pluses and minuses up and down. So nature, through whatever method, seems to have also been interested in lightweighting, and that's why like bird bones are actually hollow. Human bones, I think, are more solid, but bird bones have lots of cell structures inside. Another picture I'm showing here is some structurally optimized 3D printed suspension component for a car. And then the cars you see there, the body structure, that's some work I previously did at when I worked at Chrysler as an engineer. Okay, so why is reducing weight important? Fossil fuel use, reducing fossil fuel use, I think, is probably one of the most important reasons to reduce the weight of a vehicle. There's a lot of controversy out there about, if you reduce this percentage of weight, how much can you actually take out of the car? The number that sort of flies around is that for every 10%, or for every 10% you take out of the vehicle, you can get better mileage by 6 to 8%. So use less fuel. That's it's kind of a rule of thumb that gets thrown around. I'd have to probably do some more testing to be completely comfortable with that number. It's important to mention here that when you start driving on the freeway in your car, the effect of aerodynamics on fuel usage is much more dominant than weight. Okay, because the wind drag of the vehicle goes up with the velocity squared. So when you drive on the freeway, weight has much less of an effect on fuel mileage. So the fuel mileage that gets increased through lightweighting really is more about when you're driving around the city. Okay, maybe for airplanes, there's also a lot big issue with lightweighting there because you have to get the thing up in the air more so than you do with a car, obviously. The engineering community with the automotive engineering community has gotten so good with powertrain technology that really a lot more fuel savings can be had through hybrid technology, better burning methods when you have a car that's running fully on gasoline or diesel. And then obviously, the world has really pivoted on its axis right now with Elon Musk and Tesla, and switching to electric vehicles. The growth of popularity in electric vehicles is incredible, and I think it's gonna make a big difference in terms of cleaning up the environment. But lightweighting is important to electric vehicles too, because lightweighting, at least for most part for city driving, translates into range. For those vehicles that do burn fossil fuels, one way or another, lightweighting also results in reduced emissions. The number I've seen thrown around is that for every gallon of gas burned in a vehicle, there are 9 kilograms of CO2 injected into the atmosphere. So that's pretty crazy. If you realize that the U.S. burns about 150 gallons of gas a year, a diesel, that's 1.3 trillion kilograms of CO2 in the atmosphere per year. So if you could reduce the U.S. fleet weight by 10%, in theory, you could probably take out close to 100 billion kilograms of CO2 going into the atmosphere. So this is substantial. This would do a lot for reducing climate change, and that's why it's important. Reducing weight also saves money. You think about a water bottle. Okay, you have this normal, whatever water bottle right here from Poland Springs or whatever, and this water bottle weighs about a pound. If you launch that water bottle into space, like they do to get water to the International Space Station, it costs anywhere between $10,000 and $25,000 to get that pound up to the International Space Station. That's a lot of money. Think about that. You got obviously, thirsty astronauts up there who need to drink water. So someone's got to figure out a way to get them water. And this is one of the geniuses of Elon Musk. With SpaceX, he's been able to get that figure down closer to $10,000 per pound to get water up to the International Space Station. Even when you take a commercial flight, which you probably haven't done in a long time because of the pandemic, it takes about $1 to $10 to get that water bottle up into the air in a whatever Boeing 747 or whatever 787 or whatever airplane. And then for cars, it's much less. It may only cost 10 cents to get that water bottle down the road. But anyway, that adds up after a while. That's why you see, like, if you can take several pounds off the vehicle, whether that's a spaceship, an airplane, or car, there's real dollar savings to be had there. Lightweighting is maybe even more critical to the trucking industry because they survive by charging their customers for transporting goods, right? The more goods they can transport, the more people's packages they can transport, the more money they make. So for every kilogram you take off the weight of the vehicle, their truck, you can increase the payload by a kilogram. That's more money you get, more money you can charge. So the U.S. trucking industry has been especially interested in lightweighting, maybe even more so than the U.S. sort of passenger car manufacturers, because whereas the passenger car manufacturers have to sell cars largely based on I don't know, marketing. So people buy cars for all kinds of different reasons. A lot of it has to do with image and vanity. Okay, unfortunately, that's life. That's things work. Whereas the trucking industry is very different. Though. The trucking industry sees very real benefits from reducing weight because they can charge more for what they're doing. Any questions, guys? No? Okay. Civil penalties. So in this country, we have the National Highway Traffic Safety Association. They run the CAFE program, which is the Corporate Average Fuel Economy program. And they set, by act of Congress, they set standards for fuel mileage for the passenger car fleet. And again, the program is called CAFE, Corporate Average Fuel Economy. So the fleet as a whole has to get an average of 35 miles a gallon. So that means that if you're Subaru and you want to sell cars in this country and those cars are burning gasoline or diesel fuel, the average fuel economy among all those vehicles has to be 35 miles per gallon. And it's a lot more complicated than that. They have this thing called the harmonized average. I won't bother you with that. You can look it up if you want, but it's a complicated way of calculating out this average fuel economy. And if these car companies don't meet these requirements, the penalties are horrific. For every 0.1 miles per gallon that a car company misses in their average fuel economy, they get charged $5.50 per car sold. Now, if you figure these car companies survive on selling millions of cars, right? Like when I was at Chrysler, we might sell 3 million cars in a year. That becomes pretty big money really quick. That becomes hundreds of millions of dollars very quickly. So this is the motivation that the car companies have to reduce their fuel usage, to increase fuel economy. And it's there's a lot of complexity to it. There's what's called off-cycle credits, where if they show they're using some new technology that the government likes, then they can get some points added back to their average fuel economy. So there's some complexity here, but it is a fact that there's a lot of money at stake here if you can't meet your fuel economy. And there was an article recently, I knew this already, but there's an article recently in Yahoo, one of the websites, about Tesla, and that Tesla is able to make more money from selling fuel economy credits than they are on the cars. Okay, so what happens is Tesla, they're electric cars, right? They don't burn fuel, but they calculate a fuel usage equivalency, which comes out to be hundreds of miles per gallon. So Tesla never needs to worry about hitting their CAFE requirement because their cars on average are getting hundreds of miles per gallon. So they're able to sell their good accomplishments to other car companies for millions of dollars. And in fact, there's even a futures market now. You can trade options on fuel economy. Fuel economy credits. So there's a lot to be had here. This is turning into big business for Tesla. That's probably what's kept them afloat is the fact that they can sell their fuel economy credits to other car companies. Okay, final thing I want to mention is that reducing the weight of a vehicle improves handling, ride, and braking. This is true, but it's difficult to prove. It's difficult to quantify. When you talk about, for example, traction under braking, like how quick can you stop your car? you know, it's very easy to say, well, if the car weighs more, then the normal force is more, and then you've got more traction, so it all just evens out at the end of the day. The same thing can be said about cornering. I've personally driven, you know, maybe hundred different cars in my life, having worked in a car company, um, and you know, since I've been interested in these things since forever. And I can tell you that there's a certain feel that lightweight vehicles have. There's a certain sort of effortless with which they corner or stop that you don't feel in heavier cars. And there's only so much you can do with bigger brakes or bigger tires. There goes your weight again, right? So you just sort of mask increasing compounding. It's a vicious cycle, but it's hard to really quantify these things, and it's hard to really pin even vehicle dynamics engineers to saying these things with any kind of precision. It's kind of a fuzzy area, and the reason it's fuzzy is because I think there's a lot of nonlinear systems involved. Tires are nonlinear. There's rubber bushings that sit in your suspension system that are nonlinear. The nonlinearities of these subsystems affect the way the vehicle feels, and they react differently when the car weighs less. So anyway, I'll leave it at that. If you guys are interested, you know, you can go try a bunch of cars and whatever. You can rent exotic cars, and you can feel how these things change. I should mention with bicycles, for example, which I'll talk a lot about in this lecture, weight is where it's at. You know, when you're riding a bike and you're climbing a hill, if you got 3 or 4 less pounds, you're lugging up that hill. It's a big difference. When you're designing a car, the location of the removed weight is important. Lowering center of gravity affects handling and braking distances, or reduces braking distances, assuming all else is equal. So car manufacturers, good car manufacturers, strive to lower the center of gravity in the vehicle. A lot of times what that translates to is that they'll pay more money to take the weight out of a roof system than they would to take the weight out of a floor pan, for example, because by lowering reducing the weight of the roof, you lower the center of gravity of the vehicle, which again, like I said, translates into better stopping distances, shorter stopping distances, and better handling. You may have seen, I don't know how many of you guys are car enthusiasts, but BMW has spent a lot of money putting even carbon fiber roofs on their car. Some other cars have, like Mitsubishi, has spent a lot of money putting aluminum roofs on their cars. So this is a real world effect, and good car companies will spend money to take weight out of the roof of a vehicle, up high in the vehicle. This $22 per kilogram saved, that's a round number. That's not necessarily hard and fast, but I've seen that number paid for roof weight reduction. Some car manufacturers also make a big deal about the front to back weight distribution on their vehicles, because if you can get closer to, for example, a 50-50 weight distribution or even a rear weight bias on a car, you can reduce stopping distances because you can get more work out of the rear wheels. So car companies will also sometimes pay, like for most cars are front engine, they'll pay money to take weight out of the front of the vehicle versus the rear of the vehicle. There's even, there's been some problems, like back in the early 2000s, there was some problems with Volkswagen. They had designed a car called the Lupo that they went crazy with, putting titanium springs on and carbon fiber this and that, and basically they created a little tiny economy car in Europe that weighed 2,000 pounds or something, or less than 2,000 pounds, and they had a lot of issues with stability at high speed on the Autobahn. They actually had to add weight to the back of the vehicle in order to settle down, which is kind of sad. Car manufacturers put lead weights in the door handles, in the mechanisms for the door handles, so that when you get in an accident, the door handle, the inertia of the door handle itself doesn't open the door. So what else? The next thing to think about is that there's other factors that I guess are important when it comes to the importance of where to reduce weight. If you take weight out of the seat, for example, of the car, you reduce translational weight, which is obviously good for fuel mileage. If you take weight out of the end of the suspension system, so maybe you take it out of the knuckle, the steering knuckle, you take maybe weight out of a brake caliper, then you're reducing what's called unsprung weight. Okay, so you don't have to. So this is weight that's outside of the vehicle, that's outside of the spring package. So this is weight that is important to reduce, because then the suspension doesn't have to react all that inertia going up and down. So that can breed further weight reduction in terms of the shock absorbers you choose. So that's again a mass compounding savings effect there. And the most important weight really to reduce is the wheels, because the wheels are translational, unsprung, and rotating. So it takes inertia, or it takes energy to change the angular velocity of the wheel. Okay, you're accelerating them angularly. So there's energy that's required to do that. So when you take the weight out of a wheel or a tire package or a brake disc, that is very efficient for, or I say most effective at improving fuel mileage, when you can reduce the weight in those areas. The truth is that a lot of wheels on real cars are more driven by styling, and they do weigh a lot more than they have to. There's few car companies who take this to the limit, where they will really pay money to take weight out of wheels and potentially sacrifice styling. Any questions on this one, guys? Okay. So why are you guys listening to me? Why, I'm sitting here talking to you. How can you trust what I'm telling you? Why am I talking to you? And I'll say that I've worked at 2 different car companies. I worked at the Mercedes-Benz Research and Technology Center in Germany, in Ulm. In that role, I worked in the materials research lab, and I did research on advanced brake rotor materials. So brake rotors are important, again, because they're rotating, unsprung, and translating. We worked on ceramic matrix composite brake rotors and intermetallic matrix composite brake rotors. Ceramic, for those of you into cars, the ceramic brake rotors that you see on Porsches and Lamborghinis and Ferrari right now are sold to them by Brembo. Brembo is a big brake manufacturer, but Brembo didn't actually develop that technology. That technology was developed in that building here on the left by Mercedes. And then Mercedes built a pilot plant near their factory in Untertürkheim, Germany. And they developed the technology, and they put it on a couple of AMG cars first, and then they sold to Brembo. Now you're seeing that technology on Ferraris, Porsches, and Lamborghinis. I also worked in the Mercedes Technology Center in Sindelfingen, and that's outside of Stuttgart. In that role, I worked in the Advanced Composites group, where we developed carbon fiber and fiberglass technology that went into production, in my case, on the mid-2000s Mercedes SLK. I also worked at Chrysler in Auburn Hills, Michigan. And in that role, I was there for several different roles. I started working out there in sort of a think tank, where we explored different lightweighting technologies and then built up prototypes and got money from government agencies and so forth to develop them. I also worked as a real nuts and bolts release engineer when I was at Chrysler in body engineering. So I released 7 cars in the high volume production: the Dodge Charger, the Chrysler 300, the Dodge Magnum, the Chrysler Sebring, the Dodge Avenger, a couple other cars. These are cars that I was responsible for big portions of the body structure and launch those in high volume production. So I'm lucky, I'm very lucky in that I've been able to see multiple sides of the lightweighting equation, not just sort of the pie in the sky theory, but also hands-on research with toxic materials, and also with real vehicles, launching real vehicles in high volume production. And because of the sort of more practical part of actually releasing real vehicles in high volume production, I think I've got lucky to have a better sense of what's really possible in the real world and what needs to be done in order to get some of the more interesting, effective lightweighting technologies into production. Okay, so here's kind of the fun part of the introduction. I want to show you guys some examples of some very impressive lightweight efficient designs that I'm inspired by, at least, and just so you can maybe begin to develop a feel for what are some efficient structures, why do these structures function, why are they efficient. So the first one here is number 1. That is the primary structure of the Lotus Elise, the 1996 Lotus Elise, the first generation one. I'll talk about this in a little bit more detail in a future lecture, but they created this body structure by taking aluminum extrusions and then gluing them together with structural adhesive, and then curing the whole structure to make sure the adhesive was hardened and everything. This was not the first use of big extrusions in an automotive primary structure. The Acura NSX used them in the rocker sections first, but I guess Lotus was inspired by that idea, and they built this structure. The really, I think, neat innovation here is the adhesive, and I'll talk a little bit later about why that was so beneficial. The next structure, this is the rear structure on the Porsche Carrera GT, so the mid-2000s Porsche Carrera GT. This is I'll call it a mid-spectrum carbon fiber primary structure. And typically carbon fiber, when used in a structure for a vehicle, is used as sort of a monocoque design. I'll explain what that means later, but sort of a central tub, and things are bolted to the tub. My research indicates that there's probably overcapability there and more structure than you really need for, say, a passenger car to use a full monocoque, and there's really some very good compromises that can be made in terms of light weighting by reducing the mechanical capability of the monocoque and using sort of something in between, like this. I call this a mid-spectrum structure, shown here. Number 3, this is a suspension corner off of a Formula One. The black brake disc is carbon-carbon composite. The control arms are made out of carbon fiber. Nice structure. It's interesting to note here that the carbon-carbon brake structure here. This is these type of chemistries for a brake rotor work very well under racing conditions where you have a lot of heat. But unfortunately, they don't stop when it's cold outside at all, barely. So when we were at Mercedes, we were looking at using ceramics to make brake rotors, and we first looked at these carbon-carbon composites and then realized that the car wouldn't stop on a snowy day. And that, I think, was really the biggest accomplishment of the work at Mercedes on brake disc, ceramic brake disc rotors, is that we came up with a composition that had a higher coefficient of friction at low temperature. So that's critical to make this technology operable. Number 4, this is suspension control arms off the Acura NSX, the early 90s Acura NSX. These structures were developed using what's called topology optimization, and I'll tell you in detail what that is in a future lecture. But this may have been one of the first big applications of topology optimization, for these control arms on this aluminum control arms on the Acura NSX. The Acura NSX is the original one, not the current one. The original one was just an absolute elegant feast of wonderful lightweighting. The time they took, the things they did on that vehicle, they developed their own alloys. Maybe one of the most impressive works in lightweighting in the automotive industry. Number 5, these are the...
Can I ask a question?
Sure.
In fact, maybe I'm ahead. Number 5, how are those components forged? Are they 3D printed nowadays? Are they poured like in a forge?
No.
How are they created?
They're sliced like bread, Steve.
Oh, okay.
So these are the pedals off the original Lotus Elise. This is the pedal structure. It's made from an extrusion that is sliced up like bread. Okay, so if you look, the clutch pedal, the brake pedal, the accelerator pedal, it's all the same extrusion. It's all the same base extrusion. And this was copied on a few cars later. Porsche copied this a couple times on some of their later cars. But it's really, it's just a really clever way of making a pedal structure, you know, where, especially for like the brake pedal, stiffness is critical. So anyway, they cut them like bread.
So the design the design maximizes the stiffness and minimizes the weight with the sort of the honeycomb appearance of it. I'm trying to remember what other structure that reminds me of. It reminds me of maybe a bridge, or I'm trying to remember what it reminds me of. But its design is reminiscent of another example of lightweighting that I can't think of.
For sure. You're absolutely right. I mean, and bridges are like that. You have a structure under bending, and you have to increase the moment, the bending moment, in order to get it stiff enough. So they have to take those road surface and the structure below it and separate them, but they got to effectively transfer the shear load between the top and bottom. So they put these web structures in, right? These V's, upside down V's. And that's how they get stiffness. That's how they transfer the load from one side to another. It's I don't know if you were listening to Elon Musk's battery day, and we'll talk about this later, but you know, he's talking about using the battery casings to transfer load. So this battery pack becomes a structural member. Anyway, really, really elegant design. I think they they saved a lot of money by doing it this way than having individual tooling for individual pedals. Okay, number 6 is perhaps my favorite car at the moment, the BMW i3. Car's not selling well because a lot of people think it's ugly. I think it looks awesome, but a lot of people hate it. But it is in fact the first mass volume car made from carbon fiber. And that is an amazing accomplishment, No other car company has taken carbon fiber seriously enough to do this. Not even the mighty Toyota or Honda have been able to do this, or maybe tried to do it. But the accomplishment here is not just in the technology of using carbon fiber, but also in finding ways to reduce the cost of the fiber itself through optimizing the supply chain. They did some really incredible things where they built a carbon fiber pyrolyzation line out in Washington State, and they used hydroelectric power to generate heat to pyrolyze the fiber. For those of you who may not know a lot about carbon fiber, the way they make carbon fiber is they start with acrylic fiber, which is basically the same fiber in your white gym socks, okay, and they stretch it under high heat. They burn off some of the groups off the backbone of the carbon, they burn some functional groups off of the carbon backbone through the heat. Okay, so they're just left with a carbon backbone. Then they stretch it so that the molecules, the carbon atoms, are lined up, straight with respect to one another. That maximizes the stiffness of the fiber. But anyway, amazing piece of engineering, the BMW i3, the only mass volume carbon fiber car ever in production. Skateboards, the trucks on this particular skateboard were developed using the tool I'll talk about later called topology optimization. And then these were 3D printed by a company not far from MIT called Desktop Metals. And I'd like to 3D print my own set and make one of these. I should talk to them. Number 8, the carbon fiber tennis racket. So when I was a kid, like wooden tennis rackets were just going out of fashion. Shows how old I am. and aluminum tennis rackets were becoming popular. And then came the carbon fiber tennis racket. So this is a very nicely optimized structure, both from the materials processing standpoint and the materials usage. And it's amazing. I think about a year ago, I walked into a Target or something, and I saw a carbon fiber tennis racket for $40. So amazing processing technology. They were able to actually get the price down to this where lots of people could afford them. Number 9 is my favorite structure, the racing bicycle frame. I believe that from the structural perspective, lightweight efficiency perspective, the carbon fiber bicycle frame is the most developed structure that you can buy. These frames are mainly made in Taiwan by either a company called Murata or Giant, okay? And these bikes are just beautiful pieces of processing and structural engineering. I'll talk a little bit later more about how this is done, but these companies have gone in and they've optimized every cross section going down the length of every tube to maximize structural efficiency. And they've also put these incredible processes in place where they consolidate the carbon fibers using prepreg and pressure and steel molds and heat, and they are able to get extremely high fiber volume fractions out of these carbon fiber materials and make these frames that are extremely light and efficient. I'll talk a lot about bicycles. There's a lot about bicycles in this semester, guys. So I hope you like bicycles. Number 10, amazing piece of work. The Boeing 787. This is a full carbon fiber airplane. So the entire fuselage is filament wound. I think it's just amazing what they did there. I have yet to be on a 787. Really frustrating me. And certainly the pandemic has slowed down my ambitions. But have any of you guys been on a 787?
I have.
What was it like?
Big windows.
Yeah, that's what I heard.
Beautiful inside. I think it's the best airplane ever made. It's just an amazing airplane.
It's an amazing piece of work. Amazing structural optimization. Makes me proud to be an American. Okay. Next, steel bicycle frame, number 11. There's nothing wrong with steel as a structural material, believe it or not. And steel can still be used to make very efficient structures. In the case of bicycles, for the most part, steel bicycles are made by welding together brown tubes or brazing together brown tubes and investment cast steel lugs. But most of those structures really don't take advantage of the geometrical possibilities, the geometrical freedom that you can get with steel. One of the reasons that the carbon fiber frame, number 9 here, is so efficient is that carbon fiber affords you lots of geometrical freedom to put material where you need it. The traditional method of making steel bicycles from tubes doesn't really give you that freedom. And that's why they're not as structurally efficient as they could be. It's not because steel is necessarily bad material for structural efficiency. And there's lots of very efficient steel structures being made. This is a bike frame made by ThyssenKrupp in Germany, where they've used a very novel method of welding together some shells, like 2 halves that are stamped out of high-strength steel, advanced high-strength steel. It's a dual-phase steel, and they're laser welded together along the center. So very, very interesting technology. Structural optimization doesn't just apply to cars and bicycles and airplanes. It also applies to bridges. So here's a cement bridge that was developed using topology optimization. That's number 12. Number 13, this is a photograph that I think I took at the Porsche Museum in Stuttgart, in Zuffenhausen. And this is the body shell, just the shell from the Porsche 908. So this is from 1968. And what's interesting here, this is all made from fiberglass. And the fiberglass is so thin that you can see through it just about. That's how thin the panels were. They're like a millimeter thick. And of course, these vehicles had no safety systems barely. So if you got in a wreck, you're pretty much dead. And during that time period, a lot of people did die in these cars because there was so little protection. But anyway, interesting structural optimization with the very, very thin fiberglass. Number 14, wind turbine blades. Composites have, I think, enabled huge jumps in the efficiency or the energy generating capability of wind turbines. This blade here is nearly the size of a football field, and it is all made from fiberglass. I've recently had discussions with General Electric, and they're looking more and more at carbon fiber for these blades because it will enable them to go even longer. So they're trying to get to the point where pretty much, like, if you guys know the length of the Titanic, like, they're looking at making these blades as long as the Titanic. And you can kind of, it's crazy to imagine a wind turbine where there's 3 of these Titanics spinning around in space. But that's enabled by carbon fiber, by fiberglass, by good processing methods that consolidate the fibers effectively, by simulations, finite element analysis, structural optimization software, software that optimizes fiber placement and orientation. Amazing technology. It will pay us huge benefits in terms of reducing carbon emissions. Okay, bicycles. Back to bicycles real quick. So just want to point out something here, going back to what I said before about steel being a perfectly good material for making lightweight structures. In 1985, bicycles were the highest end bicycles being ridden in the Tour de France by the most elite professionals in the world were made from steel. The state-of-the-art material at the time was made by a company called Reynolds, and it was called their 753 alloy. And the 753 alloy was an alloy of chrome and moly and iron. And they heat treated these tubes. So they solution treated, quenched, tempered to increase the strength and the toughness of the steel. And they were able to produce steel that had, a yield strength sort of in the 1 gigapascal zone, very strong materials. And then they joined these tubes using investment cast lug structures using silver solder. And it's critical that they use silver solder because if they didn't use silver solder, the steel would coarsen or grains would grow and it wouldn't be as strong. So you have to use, it's not just about the material you use, it's also about how you put things together, your processes. The frame was about 2 kilograms back then in 1985. That included the frame and the fork. And the full bike was about 9+ kilograms. If you were an Olympian, if you were Greg LeMond, you really couldn't get a bike much better than this, no matter how much money you had. Today, in 2016, and actually also obviously in 2020, the bicycles that every pro rides in the Tour de France are made from carbon fiber. And not just any carbon fiber, they're made from carbon fiber that is pyrolyzed at higher pressure and higher temperatures for longer to get more carbon, straighter backbone, higher stiffness of the fiber. The whole frame set now, including the fork, is about 1.1 kilograms. In some cases, I think they're even lighter than that. In fact, I think the technology is there to make these bicycle frames even lighter than this. But the sanctioning bodies of the Tour de France and the other pro circuit have weight limits on how low the bikes can go in weight. I guess I'm not really sure why, for safety purposes maybe. But the whole bike weighs 6.8 kilograms. So you can go out and buy a bicycle like this for $3,000, let's say. That's a lot of money, I recognize. But there are, a sizable number of people, bike riders, who can afford that amount of money for a bicycle. But the point I'm getting at is that looking at these 2 years, looking at this change in technology between 2016 and 1985, this is remarkable. This is remarkable. I can tell you your car has only gotten heavier. This is a remarkable accomplishment, and we'll talk a lot about in this lecture, or in this overall lecture, about how they achieve this. How do they get to this incredible weight reduction? So this brings up the, I think, fundamental concept I'm hoping to get across in this overall lecture, is that designing structures or achieving structures that achieve maximum efficiency, that are as light and stiff or strong, fatigue resistant, tough, fracture resistant. In order to achieve the lightest structure, you can't just focus on geometry, and you can't just focus on materials. And what I've seen in industry is the opposite. You get materials engineers who are very focused on making materials that are very stiff or very strong per their density, but they're not really interested in how you actually design a tube of a bridge or the fuselage of an airplane or a tube of a bicycle in order to get the most out of that material. On the other hand, I've certainly seen a lot of mechanical engineers, and the reality is that there are not a lot of materials engineers at car companies, for example. I've seen a lot of mechanical engineers who really aren't necessarily interested in the materials aspects. They open up a book, they look at a table, they look on the internet, they look on matweb.com, and they look for values of materials. Oh, 6061 aluminum has a yield strength of 30 KSI. I guess I'll use that. And they don't reach further. The material scientist reaches further to say, what do you need? What can I give you? And I remember, so I did mechanical engineering undergrad, and I did materials graduate school. And I remember when I first got to materials school, one of my professors, who's now at MIT, Greg Olson, once gave me a long, nasty lecture about how bad an engineer I was because I was too busy focusing on table values and materials, and that was really the wrong way to go about it, that I really needed to focus on how do you develop materials to meet goals for strength or stiffness or fracture resistance or corrosion resistance or whatever, that the materials engineer focuses on developing these things rather than just taking what's available. The mechanical engineer should see that as an option open to them, that they can use materials engineers to better their structures, to better their designs, to get to lighter, stiffer, more efficient structures. So in the next lecture, we're going to talk about how you can actually design materials, not just look up at a table what the properties are, but actually design materials to be stiffer or stronger as a function of their density. And we're going to talk about things like the National Materials Genome Initiative. We're going to talk about a great piece of software called Thermocalc, Dictra, Prisma. We're going to talk about Ashby diagrams. These are very useful diagrams that help you narrow down materials to use for a given application. And we're going to talk about Olson diagrams, which is really part of the ICME, the Integrated Computational Materials Engineering. We're going to talk about that first. We're going to talk about that for about 4 or 5 lectures about designing materials. And then we're going to shift gears and we're going to focus on the geometry. We're going to talk about beam mechanics. We're going to talk about finite element analysis, how finite element analysis can be used to operate tools such as topology optimization, topometry optimization to maximize the efficiency of the geometry to give you the stiff structure. So the way you get to the lightest, stiffest structure is to combine geometry and materials. And that's, I think, the main message I hope you can walk away with today. So I see it's 9:55, and I guess I'm supposed to stop 5 minutes before 10 o'clock. So that's my lecture for today. Does anyone have any questions?
I have one comment, and that we will have a recitation tomorrow, which hopefully the students can bring some of their questions. If not, then I'll tell you my approach on why steel is the predominant structural material.
Oh, you can tell us now. You can tell us tomorrow.
Yeah, I talked about tomorrow. Friday is the recitation.
Well,
Okay.
iron atoms are cheap. It's just a fact. Uh-oh. What does Steve have here?
Okay. There's his bicycle.
You know what this is, Don?
I think you told me about it, what it was one time. I can't quite see it in the video here, but
Oh, sorry. That's a time trial bike made by a little crazy Swiss engineer by the name of Andy Walzer. In fact, Giant offered to buy it from me so that they could saw it up and find out how the carbon fiber layers are laid down, because it's stiff where it needs to be. And that bike is actually made just for me, not only my biology, the length of my femur and everything, but also my power output. I have to get you on it, because in terms of functional evolutionary design and light weighting, there is no better bicycle made in the world.
well, I look forward to seeing it. You know,
my chance to do show and tell.
when we actually get back to in-person lecture, and you guys are welcome to come back if you're interested. You know, I have all kinds of interesting trinkets I can pass around the room of pieces of aluminum that are reinforced with Nextel aluminum oxide fibers. We're going to bring in bicycles. I have a nice little bicycle collection. Steve does too. We can show you real world what these structures look like and how they've evolved over the past. Well, I've got bikes going back 40 years. I don't know about you, Steve, but I've got a 1981 bike that I can bring in to show what that looks like and compare that to your carbon fiber bike.
That's me too. I'm sort of a collector. Although I don't know, maybe I might give up one of them for that 908 Porsche that you saw. The picture of that. I wouldn't mind having one of those.
Yeah. Me neither. Any other questions, guys?
Yes, I have one question.
Yes, sir.
Because my family work for automobile industry, and some are designers, automobile designer, car designers. I'm just curious, like every time there is a debate, I mean, there's an argument like between designer and engineer. I'm curious, like especially for car, styling is kind of critical, right?
Absolutely.
When you have the style, I mean, you have the certain language for a certain car or family, and how do you do the light weighting process? Is there a sequence, or who should go first? Because I guess there's a trade-off, right?
Right. It's a thorny topic, no doubt. It's a thorny topic. It's hard to make everybody happy. But I've actually written on this topic about how design, okay, and structural efficiency are inseparable. It sounds like you're into car design. You know Freeman Thomas?
No. Yeah.
You know he is. Freeman Thomas was at Chrysler when I was there, and I used to hang out with him at these Porsche Club events. And he, great guy. Really like to see him again. He designed the Audi TT, so he got famous for the Audi TT. If any of you know that car, and a couple years later, he came up with this design. He called it the reverse A-pillar design. So the A-pillar of the vehicle was actually facing the wrong direction. You know, instead of going from low to high and backwards, it went from low to top and forwards. And you know, me and my friends looked at each other and almost puked, because it was like, this is going to drive so much weight into the vehicle. But at the same time, I had other designers at Chrysler I would talk to, and we would have discussions about how the shark, the fish, the animal is such a beautiful design, a shark. So I think by bringing that up, what I'm trying to say is that there's room for structural efficiency and good design that people like, that sells. Ferraris, Lotus Elises are beautiful cars, I think, and people love them, and they are very structurally efficient. So there's room for both there. Now, having said that, yeah, I've fought tooth and nail with designers back then about little tiny things on windows and stuff. You know, it's a hard balance to find. It's a hard balance to find. But we'll talk about this later, and we'll talk a little bit later about the relationship between styling, because I understand from being in a car company that like styling is such a huge part of it. people buy styling. There's just no way around that, and it's not a bad thing. I'm not saying it, but it's something that's got to be aware of. You can't, like if you remember the Consulier from the mid '80s was a very lightweight, efficient fiberglass car, but it was so ugly. It was so ugly. It never sold. That's the extreme, I think. Very structurally efficient, very ugly. Anyone else? Okay.
Thanks.
Great. See you guys next week. I'm gonna stop recording now.